Next speaker is Christopher Haruna, who's a technical project manager with the Brussels Research and Innovation Centre for Green Technology.
Yeah, okay, great.
Okay. Before I start, I would like to say I'm excited. I'm actually in Ferrari. Hello, everyone. Yeah, it's been I've been a big fan of Ferrari, so this is a special moment for me. Yes, so I'll be introducing the Haven project, and it is a European project, and it's actually the acronym for High Performance Hybrid Energy Storage System for Multi-Service Provisioning. And the project officer attached to this project is Linda Novosadova, Brussels Research and Innovation Center for Green Technologies is the coordinator, and I am the project manager. So all references or inquiries about the Haven project can be directed to me. So I would like to say I've been following the workshop so far, and I've been very inspired by the results of many of the projects that are ongoing. But I'd like to say Haven is quite a newborn baby because it's only a couple of months old. So I will be speaking more of the ambition and the objectives of Haven, not necessarily speaking about results at this stage. So I will proceed. I know you all have heard lots of projects and presentations, but allow me to bore you a little bit on energy storage before we jump into Haven. So energy storage, the basic of it is storing or capturing energy and using it later on. And there are different kinds of energy storage technologies. It could be mechanical, it could be thermal, it could be electrical, electrochemical, chemical. But I'm going to be focusing on the electrochemical technology of energy storage. And this is where Haven comes in. Haven is basically a storage system that uses high energy and high power for grid support. So it's a storage system. I would have wanted to use a little bit of a perhaps I can illustrate something, but as I go on and as I generate the momentum, I might be making some illustrations. Yes, so Haven is a hybrid energy storage solution, and it combines the technology of high energy storage and high power storage. And the novel thing about Haven is the combination of these battery technologies alongside other technologies that are innovative, like the cognitive power systems and the energy management system inbuilt within the Haven project. So the objective of Haven, or the general objective, is to basically demonstrate how the HES system can provide high energy and high power capabilities for the load or the grid, such as in this case, for example, EV charging or buildings or basically to support rest penetration. Now, let me see if I can go back to this part here and see if I can get a pen. Yes. Now, when talking about energy storage, sorry about my, it's a bit rough, but yeah, we'll get the idea. When talking about energy storage, there are two kinds of densities to consider. The high energy, the energy density, which I'll give it here. I'll make it an E, and the power density. So the energy density is, I'm doing all this because we're in Ferrari. If you have an electric vehicle right now, you want to ensure that the car has a good range. And you'll be picking a battery, or you'll be considering batteries or storage technologies that have a good energy density. And that is what will give you the range. Then, for the power, if you want a high performance vehicle, for example, you want to, like Ferrari, you want to hit those, you want to go high speed, you want to go instant power demand, then you want to look at the parts of this graph that is on the power density of this graph. So there has to be a trade-off, and this is where the hybrid energy systems comes in. It combines the advantage of energy and the advantage of power. That being said, there are 6 operational objectives of Haven. So the first operational objective is to demonstrate how the HES system can be efficiently efficiently designed to promote better usage in next generation storage technologies. The second one is to optimize state-of-the-art power conversion devices with cognitive functionalities. The third one is to develop advanced control systems and management strategies for the HES. The fourth is to develop a digital twin for the management and diagnosis of the HES. The third is to check the life cycle of, to assess the life cycle of the HES system, and to establish adequate critical raw material recovery plans. The sixth is to make sure that Haven is taken generally after the project is, or accepted generally by stakeholders after the project is completed. So the impact of Haven is for the stated here for the competitiveness in the European battery system, development of sustainable, safe technologies, and decarbonization of transport at large, and accelerated growth of innovative and competitive battery of the battery manufacturing industry. I'll go straight to the methodology of Haven now. As I had earlier explained, Haven combines a lot of things to form this this innovative solution in the storage sector. Haven combines the high energy power solution, high energy battery solution, and the high power battery solution. It combines the cognitive power electronics, which in this case would be the DC-DC converters. It combines the digital twin and an energy management system. Now, all of this makes up the Haven system. The Haven project is split into 9 work packages. And as you can see, project management and DECs run continually along the life cycle of the project. Work package 1 is the specifications and requirements, where we talked about the framework, the future trends, the KPIs, which is a sensitive information. I'm not supposed to disclose any of those here. The use case specifications, and of course, the system requirements. At this stage of Haven, we are currently just done with work package 1. So I would say we're between 18 to 20% complete. The next work package is the tools and design for management and diagnosis. In this case, we'll be talking about the EMS and the digital twin creation. Work package 3 is the construction of the novel cognitive power electronics, in this case, the DC-DC converter and the edge device. Work package 4 is the actual battery system development. Here, there will be the battery characterization and the actual manufacturing of the high power and the high energy batteries. Then work package 5 is the integration and the assembly of the HES, putting together work package 2, 3, and 4 into this HES system, as I had earlier explained. Work package 6 is the demonstration and validation of HES. Now, work package 6 is my personal favorite part of the Haven project, because this is where we actually test and see what we've done and to actually check the viability of the HES system. And there will be demos on 3 physical use cases and 2 virtual use cases. Work package 7 is the environmental and economic assessment of the business model. And work package 8, DEC 9, as I had earlier explained. So, current status of Haven is month 9. We are, at this stage, I might say approximately 20% complete, because we are just concluding work package 1. Although Haven is slated to go on for 48 months. So hopefully, if we meet by this time next year, I should have more results to give about Haven. So as I said earlier, would be validating the HES prototype across 3 different physical use cases and 2 virtual use cases to validate the hybrid energy storage system. The first use case is these use cases all tell different stories, but the point is they are going to be validating the hybrid energy storage system. The first use case is going to be enabling ultra-fast EV charging. We all know these days that the rave for EVs is the in thing. Everyone wants to have a Tesla. Everyone wants to have. Oops! I hope I didn't. Okay, everyone wants to have an electric vehicle, but using EVs or having a large amount of the demographic switch to EVs comes with its own challenges, which is stated here. Increased power demand and from the grid. This is where we will be testing the hybrid energy storage system to see how it can be a solution for renewable energy sources. For example, there is a solar panel in this place here, and we all know the story of photovoltaic systems. They're intermittent. When the sun is high, you have supply, and when there is no sun, you want to rely on your storage system. Now, if you decided to load a charging area now with EVs at a particular time, you increase the demand for power at a particular time, increasing a peak time. So at that point, you are creating peaks. One advantage of the high power system is to instantly deliver power to shave peak moments, which is one of the key services of Haven, to offer peak shaving during these peak periods. And this use case would be effectively validating the HES to see how it responds to see how it delivers peak shaving and load leveling. The second use case is the hybrid energy system, storage system supporting weak distribution grids. In this case, we'll be looking at a building facility that is composed of many companies, laboratories, and offices, and power is not stable in this in this situation. So we'll be using the HES to validate how it responds to peak shaving, to peak demand periods, and also what's the use of technology if people don't use it. In this case here, we'll be looking at how the HES can reduce costs in terms of energy demand. Use case 3 will be looking at a hybrid power plant where there will be different renewable energy sources. In this case here, you can see the wind turbines, the PV panels, and the HES system here will be testing a lot of services like frequency to see how it responds to the grid. In this case here, there will be a grid emulator in this hybrid power plant. So it effectively copies how the grid would function. So the HES will be validated in this use case, and use case 4 and use case 5 are virtual. We have a multi-microgrid system and a high-speed skyscraper. Once again, the HES would be looking at different key services in these use cases, and one of them would also be peak shaving. Also, one of them would also be backup power. We would see how the HES would respond in these use cases. So I'm also curious to see the demonstrations. So yes, these use cases are very interesting to me. We're still in the process of developing them and mapping them to see how it would go. So the use case, the energy requirements for the use cases here are stated in this table. For use case 1, the high power would be 68 kilowatt hours, and the high energy would be 320 kilowatt hours, basically on this table. However, the 971 kilowatt hours would be required for the 3 demos, and it's up to the consortium to see how the battery could one HES battery could service all the use cases. And this is where the digital twin comes in. If you have, just in case you are having a question about the virtual use cases, the virtual use cases, how would they be, how would the HES be validated in the virtual use cases? So the digital twin would be be modeling the HES in a digital format, in a virtual way, and would simulate the HES on the virtual use cases as a digital twin, and also have these results. In this case, would be validating how the HES would function if we're also using diagnostics in the project. So the outcomes of Haven would be to sorry, I'm a little I'm a little nervous, so please forgive me. The outcomes of Haven would be to improve, to demonstrate the energy storage technologies with improved performances, sustainability, and safety. To also enable levelized cost of storage, making sure that the cost of storage drops to 0.05 euros per kilowatt hour per cycle in 2030, while also reducing the use of critical raw materials. And the third outcome would be to increase digitalization from design to operation, enabling faster development and use in on-grid applications. This is where the digital twin comes in for the diagnostics and evaluation of the project. We also hope to create synergies between producers, strengthening and hope to strengthen the EU battery ecosystem at large by as an outcome of this project. And number 5 would be to establish multi-service approaches to energy storage, reducing costs. As you can see, cost reduction is one of the important outcomes of the Haven project, and also to increase reliability and resilience of the electricity system. So Haven comes with its challenges, and there are a lot of challenges which we are still trying to tackle, which we are tackling, and some of these challenges have come up as the project is evolving, and it ranges from software to hardware. And there's even a challenge that has come up with the logistics that I haven't even listed here. So, but this is where the consortium comes in, because the consortium is a combination of different experts around the world. We have partners from Africa, partners from Europe, partners from India, or experts in the field, and we are hoping that with the expertise of these partners, we'll be able to address these challenges as they come up in the project. So the future, this is my last slide. Based on the objective of Haven, if you were to ask, how does this project throw more light into the future of EV batteries? So we are looking at trying to be, as one of the objectives of Haven, which is to have more efficient hybrid energy storage systems. We are looking at a system where EVs have modular batteries, basically more using chemistries or technologies that have. Did anyone say something?
No, you're okay.
Sorry.
Okay. All right. All right. So we're looking at a future where EVs have more efficiency and incorporate not just energy storage, but also include power storage, and not just power from supercaps in this case, but power from batteries that are modular and can deliver to for high performance situations. We're also looking at reduced costs by the incorporation of modern or novel battery chemistries and advanced control systems. In this case, where we considered the cognitive power electronics within Haven, using it in an EV could also or advancing these control systems or converters in onboard electric vehicles is definitely the future for EVs. And you can follow the Haven project on social media, and I think this is where my presentation ends.